All right, guys, ready for the second one? All right, so 13B, our second exercise today is all about expected value, and you can see that we're still talking about these same tables. So it says, consider the experiment where you toss 4 coins and record the number of tails. Okay, so there is the table for us. Instead of writing probability of capital X equals little x, we will write P of X, where that means that's the probability. It's more of the notation what we're used to anyway. So probability of X for that bottom number. Which, instead of writing this, we're just going to write that, which is probably what we're more familiar with anyway. Now, the reason we're wanting to do this is we're trying to find today, this exercise, the expected value. When we do an experiment, and we did data in years 7 to 10, if we wanted to work out an average, we would just add them all up and divide by how many there are. But in probability, if we're talking about the scores that we can get when we're throwing coins and those kinds of things, if the outcomes aren't all equally likely, then we can't just do a normal average, because some things are more likely than others, and it wouldn't be a good indication, would it? So an expected value is actually what we call a weighted mean, which is written down here for you. To calculate the mean of a probability distribution, we need a weighted mean of the values to give more weight to the more likely values, okay? And less weight to the ones that are less likely. So instead of multiplying each value by 1 over n, we multiply by its probability. Okay, so there's a comparison here. There's a comparison here. This is how we worked out a mean normally. If I had the scores 2, 4, 7, 8, and 9, if I want to average them, all I do is add them up and divide by 5. Okay? But if those numbers were not equally likely, how do we then adjust for that? And the answer is that we times each number by its probability. So this one, this is an equally likely one. They're all going to have, there's just 5 numbers, and I have a 1 in 5 chance of choosing each number. So I take each score, I times by 1 out of 5. The second score, times by 1 out of 5. And I end up with the same result.
With the expected value, you wouldn't really be expecting to get 6, because that's what it does.
That is true. So what it's saying is, if you did the score often enough, that would be, while it is not one of the scores that you would get, it would be the average. So if you went and picked a number over and over and over again, that would be the average of the scores that you chose out. I know that's a weird concept because we're talking about a weighted mean here. So yes, maybe you'd expect that it would be slightly above the 7 for some of them, below for the others. It is approximately in between of where it would be. It's not one of your scores though. It doesn't have to be one of your scores. Okay. So if, like this one here, this is back to our coin. If our 4 coins, because they were not all equally likely, that table that you have at the top of the page, 0 tails had a 1 in 16 chance. 1 tail had a 4 out of 16, 2 had a 6 out of 16, 3 had a 4 out of 16, and 4 had a 1 out of 16 chance. If we times all of those together, it actually means that you get a weighted mean of 2. Okay, you are most likely to get, if you look at that table, 2 would be what you're expecting to get, your average value, your weighted mean for that, for throwing 4 coins. Okay, so we're not going to be writing it out like this though. We're going to be using a table to help us do it. So let's have a look over here, a little bit more to explain. The formula for expected value of discrete probability distribution with numerical data is the weighted mean of the values of x weighted by the probability P of x. So E of x, that stands for the expected value. This symbol here, that is a sigma Greek letter. It means to sum. X is the score times by P of x, the probability of that. The expected value is also given the symbol mu, another Greek letter, and you can see it written down here. We can also use the Greek letter mu to represent this weighted mean or this expected value. Okay. Expected value of a uniform distribution. In a uniform distribution, all the values have the same probability. We could add the values and then divide by the number of values, but it is better to continue with the same setting out. There are two things to notice here. The sample space of a uniform distribution consists of equally likely possible outcomes. These were the sorts of sample spaces that most of the calculations in Chapter 12 were based on. You know, we had all the ones where the branches were all equally likely. In a uniform distribution with n values, each value has a probability of 1 out of n. Kind of like what we're seeing with that 1 out of 5 when the things are equally likely. Thus, to weight each value by its probability, we multiply by 1 over n, so that calculating the expected value is the same as calculating the mean of the values. I know it sounds very confusing and very wordy right now. Hopefully the examples here will help to see what's going on. So we have 20 friends who go out to dinner at a Vietnamese restaurant. One has $460 cash, 3 have $370 cash, 2 have $150 cash, 4 have $90 cash, 3 have $60 cash, and 2 have $50 cash. 5 have no cash and are expecting to borrow from the others. An armed robber bursts in and seizes one of the friends at random. She threatens him, grabs all his cash, and runs away. Okay? So I get the question here is, what is the robber, based on that information, what would they expect to walk away with? It's like a weighted average. What is the most likely amount that they're going to walk away with here? I know, but anyway. So here is our table. Let X be the amount that the criminal seizes. Complete the probability distribution table. So 0 being the amount of money that they had there. How many people had $0? 5 people out of the 20. So 5 out of 20 is the probability that the thief will get $0. How many people had $50? Guys, concentrate. 2. 2 out of the 20 had $50. How many had $60?
3.
Yep. How many had $90?
4.
How many had $150? How many had $370?
3.
1, yes. Okay, now there is a column there at the end which says to sum. Now you can grab your calculators out and add all those together. What are you expecting that should be though? 20 out of 20 or 1. When you add up all the probabilities in an experiment, the total should always be 1. If it is not, it means that you've missed one of your variables in there. Okay, now that is very similar to the tables that we were looking at in the first exercise. This one, because we're trying to find an expected value, we have this extra row that we introduced. This is the x times p of x. Okay, remember that to find the expected value, there it is, the sum of x times p of x. So, if I want to find x times p of x is 0, the probability of 0, the p of x, is 5 over 20. I'm timesing that with that. 0 times 5 over 20 is 0. Then do the next one. 50 times 2 over 20. Okay, then 60 times 3 over 20. And then so on. 90 times 4 over 20 is 18. 50 times 2 over 20.
Oh no, bro.
Yeah, you're right.
Oh.
370 times 3 over 20.
Oh, I've got this.
Let him do it.
Oh, no, I don't have it. Oh, sorry.
55 and a half. And 460. Oh. Okay. So, this last remaining box if you sum all of those scores, remember me saying that the expected value was the sum of x, p of x? So if you sum those, that number right there will be your expected value. Add them all up. Yes. So $125.50. So that is how much the criminal could expect to get.
But he could never get that one.
He wouldn't get that exact number, no. Or she, yes.
I'm sorry.
Also, if she had weapons, why wouldn't she just hold them all weapons?
All right.
Yeah, but
Don't make the scenario more complicated.
because at a Vietnamese restaurant, what they have is like that those scribbles at the front.
It was a snatch, grab, go.
Yeah.
Snatch crap.
Snatch the head, I don't know, whatever it is.
Why not just snatch the handbags?
Anyway, so that is the weighted mean. So on average, because there was a different probability for each one of those, the average cost that robber would expect to get would be $125.50. Then we have to graph that distribution and state her expected gain. I've already stated the expected gain there was $125.50. So the graph. So remember that the horizontal axis is our x-axis for our random variable. And we've got increments there going up to 460. So I'm just going to go up by 50s. Okay, now for the vertical axis, which is our probability, I have my smallest probability is 1/20th and my highest is 5/20th. So let's just go up in 20ths. 1, 2, 3, 4, 5. 1/20th, 2/20th. I feel like this needs to be bigger. Can you guys see what I'm doing?
Yeah.
Good. Okay, a little bit, I know it's a bit squishy in there, there wasn't a lot of space. So drawing that on, a score of x was 0 was a probability of 5 out of 20. So right there, dot on the 5 out of 20. At 50, the probability was 2 out of 20. Now it gets more interesting because I have to go off my scale here. 60. So I'm going to put a little line in here saying that's where 60 is going to be. 60 is 3 out of 20. 90, which will be just before the 100, is 4 out of 20. 150, get to jump down here a little bit, is 2 out of 20. 370, way up here, yep, quite a big difference now. That was 3 out of 20. And 460 is going to be 1 out of 20. Okay, so that is the graph of our distribution. So you can see that we are no longer uniform. That there is a bit of variance. Oh, getting into our next exercise, because variance is talking about how spread out those dots are, and that will be coming up in C, 13C. Okay, so that is the graph. Next page, we have one more here to do. A dice is thrown. Yeah, what's up?
What is drawn on this side?
What is drawn on this side?
Yeah, the y.
This is the probabilities, these numbers here.
Oh, okay.
Yeah, probability. Okay. A die is thrown, graph the distribution and find its expected value. So when we throw our dice, our variables that we can get are 1, 2, 3, 4, 5, and 6.
Didn't say how many sides the dice have.
That's true. Okay. We will assume it's 6 unless it states otherwise.
That's not a very fair assumption.
Okay, good point. The probability. The probability of rolling each one of those numbers, we already did this in the previous exercise, is 1 out of 6. The last one on the end is going to be for the sum. The sum of all of those probabilities will be equal to 1. Perfect. Now for our x times p of x row, which is helping us to get ready for our expected value, we times the x times p of x, so 1 times 1 over 6 is 1 over 6. 2 times 1 over 6 is going to be 2 over 6. I'm not going to simplify them, do that later. 3 times 1 over 6, 4 times 1 over 6, 5 times 1 over 6, and 6 times 1 over 6 would just be 1. But anyway, when you add all of those together, that is our sum of xp of x, which is our expected value. Anyone find it?
7 over 2.
3.5, which is 7 over 2.
Yeah.
So that means that your expected value, when you roll a dice, although we know you cannot actually get a 3.5, the average would be a score of 3.5. And it does say to graph the distribution, which we've already done this. Probably don't really need to do this again. But we like our notes to be complete. We did this in the last chapter. Yeah, it's the exact same thing. Because the score across the bottom is 1, 2, 3, 4, 5, 6. And the probability is always the 1 over 6. So, yeah, we've already done this. That's the uniform, no variance in those probabilities at all, but an expected value of 3.5.
What's the one that's not uniform?